Assalamualaikum warahmatullahi wabarakatuh. Very good day to every one of you. So today I am going to continue my lecture on the last topic, which is the absorption process. For today particularly, I'm going to cover the fourth learning outcome in the topic, which will cover the material balance and calculating the number of theoretical stages in multi-stage countercurrent operation of an absorption tower using a graphical method. But before we start, I would like to show you the differences between plate tower and packed tower. These two towers, or sometimes we call it columns, are the most two common tower or column use gas and liquid absorption process. Okay. In gas absorption process, a gas mixture is brought in contact with a liquid solvent to selectively remove one or more component from the gas. So, plate tower is the tower or column that is aided or inserted with trays, okay, or structured trays, okay. As compared to plate tower, packed tower will be aided with packing materials, okay. So you can see the differences later in the next lecture. I'm going to show you the different packing materials. But for today particularly, before we started discussing on the calculating the theoretical stages, I would love for you to see the differences between the two. The application of plate tower is chosen over a packed tower is when the load cannot be handled by packed tower, or if there is any likelihood of deposition of solid during absorption process, in which we quickly choke packing materials for packed tower. So for these cases, manufacturing will choose plate tower over packed tower. Alright, so before we go further, I want to describe process descriptions of gas absorption using a tray tower. In a tray column, the gas enters the bottom of the column and rises through a series of horizontal trays of plate. Since the gas absorption process sometimes used to clean the gas stream, this gas stream sometimes is called dirty gas. Okay? The liquid solvent then is introduced onto the top trays of the column, okay, which is denoted as cleaned. If you refer to the figure here, the clean tower is referring to the liquid solvent which is introduced onto the top of the tray, and it will flow downward, okay, concurrently to the gas flow. Each tray consists of holes or perforations that will allow the gas and liquid to interact or make contact. The liquid solvents then the gas component, right? The gas component will dissolve into the liquid. Okay, liquid as they come into contact with it. Right. So the liquid solvent that is introduced will flow over the tray and down through the column, collecting this adsorbed component from the gas. Alright, so the component that of interest that we interested to be taken up from the dirty gas will somehow absorbed in the liquid flows. So absorption process occurs through the mass transfer between the gas and liquid phases. Okay, as the tray actually providing additional surfaces area and the medium for the mixing process, which promoting the mass transfer between the gas and the liquid phases. As the gas passing through the trays, it will exit the top of the column, and this gas, as you can see denoted as clean gas, is called clean gas due to the most of the component that interested to be separated from its stream is now absorbed into the liquid stream, and the liquid that containing the absorbed component is then collected at the bottom of the tower. So that's how, that is why it's denoted as the tower. Alright. Okay, so there are a few types of plates. Okay, the two types of plates that is used for plate tower: sieve plate, okay, and valve or bubble cap. So if you see any process descriptions using sieve, valve, or bubble cap, the process is actually referring to the plate tower. So the process is occurred is in the gas absorption is actually occurring in the plate tower type of column, right? Nowadays, so sieve, valve, and bubble cap is actually conventional type of plates. Okay, currently there are a few types of enhanced plate manufactured to increase the contact and surface area between gas stream and liquid stream. Right, so there are a few advantages of using plate tower in gas absorption process. The first one is better liquid and gas contact. The second one is flexibility in operating conditions, and the final is easy to control. So, but then the decisions on using which tower, which column is actually dependent on the factors such as specific application, separation requirement, as well as operating conditions. Alright, so particularly for today, I am going to show you how to solve, how to evaluate the number of theoretical stages for counter current in plate tower or tray tower using graphical method. Okay, let's see the questions here. Example, okay. Contaminated air stream, okay, contain 14% of SO2, is flowing through an absorption column. It is desired to absorb 90% of SO2 by using pure water in a bubble cap absorption column. The inlet water flow rate is 160 degrees. The inlet water flow rate is 160 kmol per hour, while the inlet SO2 flow rate is 5.7 kmol per hour. Given that the equilibrium relation of SO2 in the liquid and gas phase is Y equals to 2.5. Alright, there are a few informations that we need to address in this question, okay? Sorry, excuse me. The first one is the air stream, okay? This air stream contained 14% of SO2. So the gas flow containing air and SO2. So this is two different types of gases containing in one gas phase. Okay, and out of 14 mole percent of SO2, only 90% of SO2 is going to be separated from the gas stream by using pure water flow. And this process is occurring in a bubble cap absorption column. So when it says a bubble cap absorption column here, it's clearly referring to the tray tower or plate tower. The inlet water flow rate here is 100 degree, sorry. And the inlet water flow rate is 160 kilomole per hour. It's pure water. There is no no other component containing in the water inlet, okay, at the beginning of the process, meaning the component of SO2 or air doesn't exist in water flow rate. And the inlet SO2 is 5.7 kilomole per hour. It's not the inlet of air, it's just the inlet of SO2, sulfur dioxide. Apart from that, the equilibrium relation of SO2 given in the liquid and gas is Y equals to 2.5x. This is the equilibrium relationship. Okay. So the first step is we need to identify the type of absorption system. Which it says here is a bubble cap absorption column. They use bubble cap absorption column, meaning it's clearly a tray column or plate column. The next we need to identify the gas and liquid flow, which is the gas stream, how much is the liquid flow, and the respective flow rate. Alright, so for this particular case, the type of gas tower used for the absorption is a bubble cap absorption column, which is clearly a plate tower. The gas stream is air, which is the total flow rate is unknown. Okay, what we do know is the total SO2 flow rate, which is 5.7, and the liquid stream is containing purely water as much as 160 kilomole per hour. Okay, the next step is to construct and label the schematic diagram of the counter current system so that we have the idea what is actually what component is actually going into the system and what component how much the component is going out from the system. Okay, so we have assuming we have a vertical absorption column where we have the gas stream entering the column at the bottom, and this gas stream is a mixture between air and SO2. And on the other hand, we have a pure water, which is the liquid flow flowing downward, entering the top of the column, flowing downward of the column, and then the gas stream will go up to the top, and the liquid stream will go straight to the bottom. In the tray column or plate column, we assume there is mass transfer occurring during the process. We have another two stream going out from the column, which is at the top of the column we have air and a small amount of SO2. Okay, why do we have small amount of SO2? Because only 90% of SO2 is absorbed by the pure water, meaning 10% of the initial conditions of SO2 will flow still left in the airstream, and that's the reason why we have a small amount of SO2 in the gas stream, leaving the column at the top of the column, right? Alright, next we identify and label the molar flow rate. Alright, so here we go here. So we have the interest component that is labeled in red here is the acetone. Okay, sorry, SO2, it's not the acetone. So let's say A is the SO2, B is the water, and C is the air. So we have three components in the system. So the component of interest here is the SO2 that we need to strip, okay, from the airstream, goes into the leaving out the system at stream number one, stage number one, after plate number one, right? Okay, so we have liquid stream at the top here is denoted as L naught with 160 kmol per hour. We have V stream, the gas stream denoted as Vn plus 1, which is the combinations of 5.7 kmol per hour SO2 stream and air stream. Okay, is the combinations of SO2 stream and air stream. Okay, leaving the system is V1 is the flow rate of gas, which is the total of the flow rate leaving the system is still unknown, and the mole fraction, okay, mole fractions of SO2 in the gas stream leaving the system still unknown. Same goes to the liquid flow rate. Okay, actually liquid flow rates, the total flow rate of liquid leaving the system is the combination of liquid flow and a small amount, sorry, it's not a small amount, 90% of the SO2 from the stream. And the mole fractions of SO2 in the liquid stream is denoted as XAN. Still unknown. Right. So next step is we need to determine the flow rate of the inlet air and as well as the flow rate, so that we can evaluate the mole fractions of SO2 in the gas stream. So we need to evaluate the total volume of the gas entering the system. Okay, and this total the small amount, 10% of the SO2 stream will contribute to the total gas stream leaving the system V1. So we need to know the air stream so that we know how much amount of the SO2 is actually leaving the system in gas flow in the air stream. Right. So we need to know the flow rate of inlet air. As we know, the total gas flow rate entering the system is the combination between air stream and SO2. So Vn plus 1 is actually air stream and added with 5.7 kmol per hour. But we also know that SO2 flow rate is actually 5.7, and the mole fractions of SO2 is 14 mole percent. So meaning this 14 mole percent of total flow rate will contribute to 5.7 kmol per hour. Okay, sorry. So total gas flow rate is calculated by just dividing 5.7 with 0.14, will give the total flow rate of the air going into the system entering at initial condition at the bottom is 40.714 kmol per hour. Therefore, the flow rate of air only entering the system is 1 minus 0.14 because 1.14 is the SO2. So the air is 1 minus mole fractions of air in the system entering the system at the bottom of the column is 1 minus 0.14 of total flow rate, which is 0.86 times with 40.714 give us 35.14 km per hour. So the main idea here is to determine the theoretical stages. What to do is we require an equilibrium line, and this equilibrium relation of SO2 in both liquid and gas phase is given as y equals to 2.5x. So the best way is we using graphical method. We need a graph and we need to plot, okay, to draw this equilibrium line on the graph. Okay, we assume when x equals to 0, okay, we find to draw the equilibrium line. The best way is to decide two point, initial point and final point. Okay, so let's say when x equals to 0, this equilibrium relation will give us y equals to 0. And when equals to x equals to 0.06, y equals to 0.15. Alright. Alright. You might need to ask how to decide to choose at 0.06. Right. So in general, we only have 14% of SO2 in the inlet stream, which we need to absorb as much as 90% of it. So what is left in the gas stream is 10% out of 14%. So somehow it gives us an idea that the small amount, the exit stream is actually containing only a small amount of SO2 mole fractions, right? So from there we can just guess, choose a value, small value that smaller than the possible exit stream. Okay, so if we have a graph here, right? Okay, the exit stream only containing, for example, like this. If we take out all the 100% of 14 mole percent of SO2 from the airstream, the highest mole fraction is 14%. 14 mole percent. That will be the highest. If we take out 100%, there's no more, 0% of the 14 mole percent will come up in the exit stream of the gas flow. Okay, so if the best possible is in the case where we only left 10 mole percent of SO2 in the exit stream. Okay, so it's more or less 0.1. All right, so we plot the graph and we pick the range within the range 0 to 0.1. Okay, so as we already decided that the equilibrium line, to plot equilibrium line, we need to coordinate. Okay, the first coordinate is when x0, y0. Okay, so it's located here in this graph. The next coordinate is when x 0.06, y 0.15. So it's located here. So we just connect these two dots to give us the equilibrium conditions. Right. The next one is locate the compositions. Sorry, it's not certain here. Composition of SO2 at the top of the tower, or denoted as SA0 and YA1. Alright, so we need to do some calculation to find the mole fractions of SA0 is actually 0, which is we don't have the composition of SO2 in the liquid stream. But we need another value, which is the composition, the mole fractions of SO2 in the gas stream, leaving this. We need to calculate the mole fraction of SO2 in the gas stream, which is YA1. So this is the mole fraction, which is 10% of 5.7, divide with that 10% added with gas or air stream. Okay, 35.014, which give us 0.016. So we need to locate this point, which is here. 0, x equals to 0 and y equals to 0.016. The next one is we need to locate the compositions of acetone at the bottom of the tower, xan and yan plus 1. Xan is mole fraction of SO2 in liquid stream leaving the tower, which is 90% of 14 mole percent, which is 90% of 5.7 added over with 90% of it plus 160 kilomole per hour, which is 0.031. And we know that the initial compositions of SO2 is 0.14. So we need to locate this this coordinate 0.031 and 0.14. X equals to 0.31 and y equals to 0.14. And we just draw a straight line in the idea that the additional of the flow rate is not much, and this line will give us, these 2 points will give us a straight line. So final step is to draw the stages, started from the top composition, which is at the bottom of the graph. Okay, which is give us first step, second tree, the third tree. Okay, so we still have some small here, which it will give us a complete triangle, but will give us a fractions of the stage. Okay, so since xan is 0.31, okay, so the process should stop here, but the stage is not definite 3.3 stages. We need to evaluate the fraction of the stage here to give us exact number of stages required to separate the process. So we need to do some fractions, which is actually a one box out of 11 total 11 box. So it's the fractions of the stage is 1/11, which will give us the total stages 3.09 stages. Okay, that is how we actually evaluate the theoretical number of stages for counter current plate tower using graphical method. Okay, thank you.